Aloha! In this 8th lecture in our Acids and Bases series, we discuss metal cations and their ability to act as weak acids. It's the small, highly charged metal cations which are the most acidic, and what they are doing is they're acting as Lewis acids, which are electron pair acceptors. But it's interesting how they work. When you have a metal cation in solution, what happens is the surrounding water molecules like to attach to it to form a hydrate complex, and that attaching is the metal ion acting as a Lewis acid. But after the molecules of water are attached, that larger complex can then go on and release a proton in solution, which is an Arrhenius acid. So metal cations, which are small, highly charged, such as chromium +3 and aluminum +3, when dissolved in water, they form these hydrate complexes, and those complexes act as weak Arrhenius acids. So here's a diagram of one of those complexes, and you can imagine how this forms. Suppose you have a chromium +3 that just dissolved in water. It's a very small, powerful, positive charged ion. And, being small, the water molecules are able to get close to it and bond to it more readily. And since it's very positive, the water molecules will orient themselves so that electronegative oxygen atoms are pointing to the metal cation. So all the oxygens are pointing to the metal cation. Now, metal ions like to have 6 water molecules surrounding them for certain reasons. And when a water molecule attaches to it, the electron pairs on the water molecule, on the oxygen atom, are kind of associating with the chromium +3. So the attaching of the water molecules is kind of like chromium +3 accepting an electron pair. So that's the Lewis acid there. But this complex, that high positive charge on the chromium ion, is pulling all the electrons towards it, and therefore away from the hydrogens on the outside, making it easier for an H+ to leave. And so another water molecule which is nearby can kind of complex with a proton to form a proton in solution, leaving the conjugate base of the hydrate complex. So here's that water with the proton detached over there. So that's kind of how they work. This large complex which forms can release a proton in solution. And so these hydrate complexes have Kas that are associated with them, and you can look them up. Now, here's a list of Kas, just a small list containing 4 metal ions. So aluminum +3, which forms this complex right here, has the corresponding Ka, 1.4 × 10⁻⁵. Now beryllium +2, that's a lesser charge, and it does this also, but its Ka is smaller. It's the higher charge ones that have larger Kas and the smaller charge ones which have smaller Kas. So, chromium's Ka is 1.6 × 10⁻⁴. So we can write this as the corresponding chemical equilibrium right there. So here's the chromium hydrate complex, and it releases a proton in solution to form the conjugate base of that complex. So you have 5 waters and 1 hydroxide, and now the charge is only +2. So this has that Ka, and we can solve for the pH of such systems. So let's do a simple example. Suppose you're asked to find the pH of 0.731 molarity aluminum chloride. So this is aluminum chloride, and there are 3 chlorides, therefore the aluminum is a +3. And it tells you the Ka of the aluminum chloride hexahydrate complex is 1.4 times 10 to the minus 5. And that's found in the table right there. So there's the Ka of the aluminum plus 3 hydrate complex. Now, when the molarity of aluminum chloride is 0.731 molarity, all of the aluminum and chloride ions are dissociated. And it's appropriate to think of all of the aluminum ions as being complexed as the hexahydrate complexes. So really, if you have 0.713 molarity aluminum chloride, that means you have 0.731 molarity aluminum ions, and also 0.731 molarity of the aluminum hexahydrate complex ions. So the hexahydrate complex is what acts as a weak arrhenius acid, and here's the equilibrium that it undergoes, releasing a proton. And the concentration of the hexahydrate complex is 0.731 at the beginning, and ignoring autoionization of water, and there's nothing else there, so no products yet. To get to equilibrium, it loses X amount, and you gain X amount of products here and here. So at equilibrium, these are the concentrations. In this expression right here, this equilibrium chemical equation has the corresponding equilibrium constant equation right there. So you take these equilibrium concentrations, you plug them in on the right-hand side, you take the equilibrium constant, 1.4 times 10 to the minus 5, and you plug it in right there. And this is the equation that you're left with. So you can use the X's small approximation to solve this, because 0.731 is more than 1,000 times bigger than the equilibrium constant. This is about 10 to the minus 1, that's 10 to the minus 5, 4 orders of magnitude. So it's safe to ignore that X right there, and it makes it simpler to solve. And so solving for X, that will be the proton concentration. It comes out to 0.0032. And now we can calculate the pH as the negative log of the proton concentration, and the pH is 2.49, which is roughly 2.50. So that's how you deal with metal cations, which act as weak acids. In our next lecture, we'll discuss polyprotic acids. So stay tuned for that. Aloha.